Is there, everyone got a handout there? Anyone not have a handout? There's a few handouts circling around. If you just put your hand up if you don't have one, and then, because then sort of circulate them down this way. There's a... Thanks. And the handout has 4 parts, and it looks terrible, but we'll kind of build it up slowly over the class, okay? And I've decided that I'm going to go a little bit slower on this idea of inverse inference and the notion of uncertainty. So we probably won't get into mixed strategies today, but the basic kind of building blocks we'll use from today, which will be these probability weighted averages, we will use with mixed strategies and probably for about three more of the lectures, okay? So we're going to develop a little kind of graphical tool to help us think about probability weighted averages. Now, what I decided was yesterday's class, we had this diagnostic question, okay, where a test came back from a radiologist, and you had to decide whether or not you thought the person had breast cancer, okay? So there's some kind of underlying disease which is very difficult to observe. I mean, you can go and do all kinds of radical surgical things and cut apart tissues to try and detect cancer, but on the other hand, you can do some sort of simpler stuff, which is kind of a diagnostic test. And then what we did is what I did, was try to walk through a way of thinking about your uncertainties in that kind of problem. We could think of the players, we can think of what they can do, what their information is, and what their payoffs are, and we say, well, forget about the payoffs for a second, okay? Let's just think about this information idea and how you could incorporate various bits of information to help resolve your uncertainty in a game. And so at the end of the class, I kind of left you with a picture that looked something like, I think it was this one here. And we talked around these numbers and this little truth table. And instead of continuing on with that particular example, because the numbers like 922 and 70, and they're difficult things to calculate with, I thought I'd just put together a little bit simpler example and something maybe a little bit more relevant to your own situation in life, and that is, oops, that one there, yeah. Educational testing, okay? So basically what's going to happen is you guys are going to come out of here at some stage with a degree, right? Hopefully. And you're going to go into the job market and you're going to take this degree, and employers are going to look at your CV, and they're going to look at your courses, and they're going to try and take that information and figure out whether you're a good employee or not, okay? And they can't really tell whether you're going to be a good employee. That's kind of uncertain. It's going on in the future. What they have in front of them is some test results, some educational test results, just like the diagnostic thing. It's a test, okay? And before you take the test, you could sort of think, well, I don't know what the test could be. You know, I can do this test and I can get a 90%, or I can do that test and get a 60%, or I can fail. You know, there's a whole bunch of grades on your transcript. The employers will be able to look at those kinds of things, but before they look at those, they'll be sitting back thinking, you know, how am I going to choose employees? Well, you know, I'd like to get an employee with good ability, but how am I going to tell whether they've got good ability? Well, what I might do is make them take a test. Okay, the test could be to go through university, or it could be an aptitude test. Now, these kind of problems where there's some kind of underlying thing which you really would like to know that's important to you, but you can't observe very easily, if at all, whereas other ones, there's a signal or a bit of information that you can use to tell you something about the thing that you really don't know but you're interested in, okay? And that kind of paradigm is what we were doing yesterday. And it's something that you've got to get a handle on for game theory, because the whole signaling idea and screening idea, when we look at strategic interaction and uncertainty, is that there various people will have private bits of information. You know what your abilities are, okay? You know whether you can work hard. And, I mean, you only have to have some friends, and, you know, like I said, this friend in high school, this guy got A's. He never did any work at all. Didn't matter if it was physics, biology, English, history. It was just like he could do it all, okay? And you look at these people, and, you know, I have to put in a lot of effort I get reasonable ability, but I have to put in a lot of effort as well. And there's some people they're just very, very able people, okay? And there are other people, there's shades of not being able, and I want to make it nice and binary, just simplify it, okay? You got an able person, or you got a less able person, okay? And or an able worker or a less able worker. And then you have all these test results which you could use, and you want to think of these tests. I mean, you'll have big banks of questions, and some psychologists or educational testers will come up with a score for you at the end. But if you just boil it down, you could say, well, you got a very good result or you got a bad result. Okay. Now, notice that process is simplifying a lot of complexity. Just saying there's two things that matter. There's the underlying ability, and there's the test scores that you're going to get. But the thing that matters to you, if your employer is, I'd like to know this guy's ability. The test score is, well, could be good, could be bad, but mostly I want to be able to find an employee who's got good ability. So if we set the problem up this way, you can think of your uncertainty in terms of possibilities. Okay, now that's a step in the right direction. At least you're not saying, oh, there's a guy who's got a suit on, or there's a woman with in a nice dress and skirt, and they look really cool. Oh, they must be good, right? So you don't just realize, well, no, I don't really know what they are, what their abilities are. So you recognize there are various possibilities. So we've got a high ability or a low ability, and then when we're thinking about test scores, you can have good test scores or bad test scores. I mean, there's a whole range in between, but let's just take the binary ones. Okay, so you've got two things that you worry about: ability and test scores. And each of those variables or things you're interested in has two logical possibilities. But if you put them together, what we look at the possibilities together, we have four logical possibilities. And we put those together in what we call a truth table. And I think this truth table is a very helpful device for getting your head around something that's a little more complex. Well, I don't know this, and I don't know that. Well, there's four things that you're uncertain about, okay? There's the person's ability. I don't know, what is their ability, good or bad. There's their test scores. How are they going to do in a test? I really don't know. And then you're uncertain as well about the relationship between the ability and the test score. Okay, so there's kind of the whole basket of uncertainty is once you open it up to say, well, not only do I not know their ability, I don't know what their test scores are going to be like, and then what's the relationship between test scores and ability? I mean, if I knew their test scores, would I know anything about their ability? Or if I knew something about their ability, would I know anything about their test scores? Okay, now, I want you to keep that kind of complexity in mind when there's two things, two variables you like to take account of, and one of them is important, and we call that a state variable, okay? And the other is, well, it's a signal for the state variable. It tells you some information, but it's unreliable information. You're uncertain about it, okay? You're uncertain about the state, you're uncertain about the signal, and you're uncertain about the relationship between the state and the signal. So that's kind of the idea that I want to think about. And so what I did is I put in some simple numbers to start off here. Now, remember, these numbers that we're thinking of are going to calibrate our uncertainty, our beliefs. And yesterday I talked about the idea of, well, your beliefs should really be your willingness to bet. Well, most of the time you don't know. So I don't want to bet because I really don't know anything about this. Okay, but for the moment, let's just sort of start off and say let's play with some numbers and see what how we might think about this kind of problem. So I picked a pair of kind of simple numbers, and I thought, well, let's make the numbers add up to 100. So we're going to think of as if we had lots of information, like with the diagnostic testing yesterday, with the radiologist, with the breast cancer things, that somehow there's a bunch of information in the background that looks specifically, at the cancer, specifically the test result, all this nice stuff back there. Well, let's imagine we have that, and what we have is sort of 100 pieces of information, and we break them down like this. You think, well, there's about a 60-40 chance on being low ability, or if you like, the chances of high ability are around 40 out of 100. The chances of low ability are 60. So I'm just bracketing these two columns because they're the columns that represent where your ability is high, where the proposition, the person's ability is high, is true. Okay, and that gives us a 1. These other columns with the 2 zeros at the top are representing the truth value of the proposition, his ability is high. Well, it's false. Okay, it's 0. That means the truth value is 0. So if it hasn't got high ability, there's only one other logical possibility, that's low ability. And we've got 60 out of 100 of those. So the way we start thinking about this, we say, well, let's think about ability. Okay, so you're looking at the ability of the students in the class. You think, well, 40% are going to be able, highly able, and 60% less able for whatever this job is. Okay, and we call that the prior information. And the idea of your prior is it isn't taking account of the signal. Okay, it's just saying this is what I think the abilities are. Then the next thing you might do is you might start to think of, well, what about able people? How will they score on tests? Okay, and what you might think is, if your ability is high, the chances of getting a positive test result are pretty good. Okay, so that's like a qualitative thing. It's pretty high. So we'll put a number on it, about 90%. Okay, now notice I put in purple here. I'm trying to keep. This is your probability. You're a player in this game. These are your probabilities. You're trying to explore what these probabilities are. You've come up with one which says, well, I think my probability of just picking out a high person from this bundle of a high ability person from this bundle of 100 is 40 out of 100. Okay. On the other hand, if I did have a high ability person, I could find them, I could identify them. So that's to the right of this vertical line, we say, if I knew that for sure, okay, that I had a high ability person, what are my chances that they would score well in a test? And I think, well, a test should be designed. These guys who do the psychometrics, they must be able to design tests that surely people who are highly able would score well. Okay, so what I thought is, let's make the score well be 90%. And this other probability, now notice we're thinking about the relationship between the test and the test and the aptitude, the state and the signal. Okay, we're uncertain about what that relationship is, but what we're thinking about is, well, if a person is of low ability, they could do well in the test, but let's make it 50-50. Okay, just a little bit better than a coin toss. If you're highly able, then we think the relationship between ability and test scores. Okay, highly able people will get good test results 90% of the time. Okay, or 90% chance. Or we're willing to bet 90% if we could identify those high ability people. On the other hand, for low ability people, sometimes they'll do okay, sometimes they won't do okay. We just take it as a toss of a coin. Okay, so that's how we're going to think about beginning to structure our uncertainty here. And what I did is I took these numbers and I put some counts in these various cells. So if you look at this, there's 40 who are highly able. 90% of them are going to score well, so they get a positive test result. So I put a 36 there. Okay. The other 10% of 40, which is 4, they're going to get a poor test result. Okay. So some of the highly able people will score poorly, but most of them are going to score well. If I look at the less able people, I want it 50-50, so I divide the 60 into 30 in this column, 30 in that column. Well, what's this column? This is the people of low ability, and they get a low test result. This is the people of low ability, and they get a high test result. Okay. Now, why is that the case? I don't know. It's just part of the test. Okay. I'm uncertain about it. This isn't a very reliable test. Okay. What you really would like a really good test, right, would be one that says, okay, the able people, all of them are going to do well. Okay. If you're able, you're going to do well on it. And if you've got low ability, you're not going to do well at all. That would be a really good test. But this is an imperfect test. Okay. You're uncertain about that relationship between this ability and the test result, or the signal and the state. Okay, with me so far? We're starting up to try to build up, explore our uncertainty. You know, we're not really sure this is 40 and 60. We don't really know whether it's 90 and 50 exactly, but let's just play with these numbers and see what we come up with. Now, if we go down to our little game tree, what we're interested in, now that we've sort of structured our uncertainty, is what are we going to do if we see a positive test result? What are we going to do if we get a negative test result? And by do here, I mean, what are we going to believe? Okay. Generally, I think that there's a 40% chance in the population of having high able people, but what if I see a positive test result? What should I think then? Okay. Generally, I think there's a 60% chance of low ability people in the population, but what if I see a bad test result? What should I think then? Okay. So we call these idea is inverse probabilities. And I put them down over here. Now notice there's 1, 2, 3, 4, 5 different ways of thinking about our uncertainty here, okay? But the idea of the ones on the bottom is that these are, if you like, inverse probabilities to these ones on the top. Okay? The color coding helps you keep track of what's inverse to what here. But what we've got here is the probability of getting a positive test result given you've got high ability. Down here, what we have is the probability of having high ability given you've got a positive test result. Okay. So this probability is an inverse to that probability. Okay. My uncertainty, I'm uncertain about the relationship between test scores and ability, but it goes two ways. Okay. If I knew your ability, I make some statement of my uncertainty about your ability to score well on a test. That's one way. The other way, which we call the inverse way, is I see your test result, but I'm still kind of uncertain about what your ability is. Okay, so you've got a two-sided uncertainty going on here. Now, this stuff is. I think this idea is important because what we tend to do is we sort of think too kind of linearly, and we make it black and white and really simplistically. And what we're trying to think here is, well, it's not just your ability, and it's not just your test score, but it's a relationship between those two that I'm uncertain about. Now, that relationship you can look at two ways. Given the ability, what's the chance of having a high test score? Given the test score, what's the high chances of having a bad ability? So the first thing to do is just grasp that concept, okay? That there's two sides to that uncertainty between these two variables. You can look at it one way or the other. Let me just back off from this example for a second. A few years back, the police had this policy of wanting to put stickers on cars about whether or not people, was it under 26 or under 25, were allowed to drive in the car. And their reasoning was, they said, look, we're really worried about car theft. And basically, when we look at all the people who steal cars, they're all young people. Okay? And it's probably true. I mean, in the sense that, there's a whole spectrum of people. There are people like me that are older. Well, I don't steal cars too much, but younger people tend to, okay? So they're looking at their police statistics, and they're saying, look at all these criminals that are stealing cars. Most of them are young. Oh, my God, look at it. All these young people are bad people. They're thieves, okay? Well, hold it a second. It's like there's stealing a car, and there's being young. There's two things. What's the relationship between those, okay? They've got information that says, oh, those people who steal cars, they tend to be young. But do young people tend to steal cars? No, I mean, you need to ask that question. That's what the kind of reasoning we're thinking about. There's two things you're interested in. You can look at the uncertainty about the relationship between them two ways. Yes, it's probably true in the police statistics that most of the people who steal cars are young. The old guys, they go hire the young guys to steal cars and they flog off the parts or whatever it is. I mean, who knows the way organized crime works. But just because there's a high chance that if a person is a car thief, they're young, it doesn't mean that young people are car thieves. Okay? If you're young, you're going to be a car thief. Those are inverse probabilities to one another, okay? Think about that. So that's, I mean, to me, this kind of inference and reasoning between two variables is something we all stumble over. This example from the doctors yesterday is, there was some famous psychologists and behavioral economists who are, they're kind of worried about how people think about uncertainty. And virtually something like 60 to 80% of doctors answered that question that we looked at yesterday. And they're thinking, they've got a positive test result, really high chance they've got breast cancer. But we saw yesterday that there were 77 people who had positive test results, and only 7 of them had breast cancer. And that's because there aren't very many people in the population that have breast cancer, okay? I mean, it's a really serious disease if you have it, but, in a certain age range, not too many people will have it. So where are all these positive test results coming? Well, that's because there's lots of people who don't have it, and the test isn't very good. Okay, so you're going to get lots of people, in that case it was 70, out of something like 992, floating out with these bad test results, and these people will make serious decisions about their life. Okay, you get a positive mammogram that's telling you, you got breast cancer, you're going to get worried. You're going to do stuff. And I mean, I have personal experience with this because I
I had a blood test that showed up a little protein that indicated I had prostate cancer. This is about 8 years ago, and I think, 3 weeks until I had the biopsy, I was a basket case, basically, because I couldn't get it out of my head. You know, I got my motorcycle accident, I got my back collapsing, you know, marriage breakup. What more? God, kill me, you know. Literally, because the worry about, you take this information, and it's very hard not to embrace it and say, oh my God, I had a positive test result. You know, I must have the disease. And that's why I encourage you to read this Gerd Gigerenzer article, because that's what he's looking at, these diagnostic tests. And he tries to really put a human element on it. And the mistaken ability we have or mistakes we make in reasoning about this, it's just like that police example, okay? I'm sure that most of the car thieves are young. But I'm also sure that, most of you people, I don't think, there'd probably be 0 car thieves in this room. Maybe 1. But we won't ask who you are, okay? Okay, I confess. When I was 16, I did steal a boat, and I did get caught, okay? But it turned out to be one of the best things in my life, because I went to juvenile court, and my friends were big guys, and so they got handcuffed. I didn't get handcuffed. I was a little guy. I was all right, see. But, boy, I was terrified of my dad. I went through we didn't actually get a conviction, but they said if anything happened to you up to the time you're 18, then you're going to get a conviction. Otherwise, we wipe it. And so I'm really glad for that now. I was one of those guys, I learned really quickly, okay? It's like, oh, I shouldn't have done this, you know. And so I didn't steal a car, though. It was a boat, okay? So it's true, or it's false that I stole a car. But I want you to think of these things. This inverse stuff is important, okay? There's 2 things that are going on. We have some simple little signaling kind of games. We'll use this education. There's a model of educational signaling that we'll use about whether a little more abstractly, using the game theory idea, but it's going to put the same thing together, okay? There's some sort of signal you can give out. The employer doesn't know your ability, and you've got to look at what's the relationship between the ability and the signal. Mm-hmm. You know? Well, high ability, something signal. You got to look at it 2 ways. I just want you to keep that idea in mind. So this little table with these numbers is a little bit easier to work with, because let's look at these inverse probabilities, okay? What have we got? Well, how many people out of this 100, when we're thinking this way, actually have positive test results? Well, here's the column. It's true you got a positive test result. It's true you got a positive test result. These positive test results come from high ability people. These positive test results come from the low ability people. And so we got 66 positive test results, okay? Or if you divide by 100, we got 66% chance of getting a positive test result. But given you've got a positive test result, what are your chances of abilities being high? Well, it's 36 out of 66. So let's put that in here, okay? Let me walk you through how we got that number. We're just using this table, and this table is breaking down our uncertainty. You know, there's like 100, if you like, observations or bits of information where we've accurately measured the ability and the test result. And, well, 66 of those come up with positive test results, but a little more than half, 36 out of 66, a little more than half, it's about 58%, okay, are high ability. Now, we call that a posterior. Sometimes in the Bayesian statistical terminology, they call that a posterior, but it's really a posterior belief. But your prior belief was 40%. Okay, we started thinking, okay, generally the ability in the population is about 40% able people, but I get this test result and I change my beliefs. Okay, I have a new belief now because I've seen the result of the test. If the test result is positive, then the chances I'm now going to put on a person having high ability is 36 out of that 66. Okay, add these 2 numbers up because they're the ones. These counts here, there's 66 who have positive test results. 36 of them are of high ability. But notice the other bit of information. It could be you see a negative test result. What should you believe then? Okay, there's 2 things you can 2 bits of information you can get out of the test. One is a positive test, but you can also get a negative test result. The person scored poorly on the test. What should you think? Are they just a smart person who didn't do very well, or are they a low ability person? Well, have a look. The people who have low test results, or they don't have, it's not true that they have high ones. There's 30 plus 4 34 of those. 4 out of 34 are of high ability. So 4 to 34, what's that, about, what have we got, about 10 or 11%? So we were thinking, gee, there's 60% chance of people being low ability, but if we saw a low test result, we'd now put almost a 90% chance in the person being low ability, because we put a 10% chance in them being high ability. Okay? Got the idea? So the inverse probability things are the ones that we really want to know. Where we're moving out along this game tree here, there's a, sorry, I didn't change the symbols here. There's a high state or a low state, which we can't observe. The blue player is going to give out some sort of test result, a positive or a negative. When all we can see is two positives, we're sitting here, we can't tell. But one thing we can tell is we have seen the positive test score. What should we believe when we get to this point in the game tree? Well, if you get to that point in the game tree, now you should believe that the chances have gone, if they got a positive test result, the chances have gone up to about 36 out of 66, about 58% instead of 40%. And here, if you get to this position, a negative test result, what are the chances that they're of high ability? Well, it's pretty low, only about 10 or 11%. It drops way down from 40%. Okay? So the idea of what we're going to do is when we draw little game trees, we have our information sets, we're going to ask, what should the person believe when they get to this point in their information set? That's kind of the whole point from the game theory thing. Okay, you with me there? All right, now I want to take this idea of just exploring this kind of uncertainty you have, and let's play around with these numbers. Because I'm not sure that it's 40 and 60 or 90 and 50% where I get all these little numbers here. Let's play around with it a little bit. What if I took the 60 and I thought, well, if you're of low ability, it's not really 50-50 you're going to score well on this test, because the test is better than that. If you've got low ability, you're not going to have as good a chance as scoring a high result. So we'll drop it down to 40%. And I put over here the opposite, which is 60%, which is the chances of having a bad test score. Okay. Now, this number up here, we call the sensitivity of the test. This number down here, we call the specificity of the test. It's taken me about 4 years to get my head around those two labels. Just remember, there's two things. You can have a good test result or a bad test result. And it's what do you learn about ability of people from those test results. There's sort of standard names that go with these things. Sometimes these two probabilities are called likelihoods. And the idea of the likelihood is an assessment of, given the state, what are the chances of getting a particular kind of signal? Okay, and that's what these ones are here. Whereas the inverse probabilities are, given the signal, what are the chances of the various states? Let's go back to these new numbers. Okay, these new numbers are saying, supposing the test is a little bit more discriminating. Okay, if you're low ability, it's going to give you less of a chance, 40%. So what I do here is I take 40% of 60, it's 24. And 60% of 60 is 36. Okay. And, well, matter of fact, I could keep changing the specificity. Even better test. It's like now if you're of low ability, it's only a 30% chance that you're going to get a good test result. So I take 30% of 60, which is 18, and 70% of 60, which is 42. Okay. Or I can make it even more specific test. I'm saying, yes. Sensitivity, more specific test. Okay, given this ability is low, the chances of you getting a positive test result now are only 20%. A low ability person is not going to do well in this test. Some do, but only 20% do. The other 80% don't. Okay, and so I take my 20%. 20 times 60 is 12. 20 times 80 times 80% of 60 is 48. Got that idea? So we could keep going through that, and we're just sort of thinking about our uncertainty here. What kind of uncertainty could we have? Well, what we're doing is we're keeping basically the same proportions of ability in the population. We're just thinking about the reliability or unreliability of the test. When it's 50-50 that a low ability person is going to pass this test, it's like they give a driver's license exam, and sometimes you think, well, basically any dork could pass this thing. It's just, well, That's not a very good test, right? What you want is, people who've done the homework, done the practice, have high ability, they're going to pass. And people who haven't done the homework and at low ability and low skill, they're going to fail. You want the test to be discriminating, but it's not for sure. Okay. So if we, you okay with these sort of counts? We're just putting in various possibilities. Okay. Now, remember, supposing we take, let me get rid of these two here. So we just concentrate on this one here, where we've got a 40% chance of a low ability person passing the test. A little bit better than 50. It's a better test for discriminating than the 50-50 one. And let's see how these numbers change here. Well, what do we have? We've got 24 plus 36, which is 60, gives a positive test result. And 36 plus 4 is 40, give a negative test result. Okay? And so 4 out of 40 will be of high ability. Whereas this one was 4 to 34. Okay, so that's going to be a smaller number. And over here, we have 36 and 24. That makes up to 60. And we have 36 out of 60 instead of 36 out of 66. So I'm going to plunk those numbers there like this. Okay. So our inverse probabilities change too. Let's do the next one. We take the 70% one. What do we have here? Well, positive test results, we have 18 and 36 is 54. And so 36 out of 54 instead of 36 out of 60. Well, that'll be our new belief. Since we've got this a little bit better test, it's going to be, what did I say, 36 out of 54. That's a higher probability than 36 out of 60. Now, if we look at the people who have the negative test result, we got 42 and 4 is 46. We got 4 out of 46. Again, that's a smaller number than 4 out of 40. Okay, so we'll put those numbers in. And so notice what's happening here is we're picking up better and better, more specific tests, better tests, and at the same time, what we learn as we move along this game tree changes. Our beliefs are going to be changing more. Okay? So take the 80% one. Let me plunk these numbers in to see if we get these inverse probabilities. I mean, this is why it's nice to have a calculator, okay? And I'm not going to expect you to do this kind of thing in an exam. I want you to get a feel for, okay, if I had to calculate these things, I probably could do it, okay? Just be able to try to think about the inverse probabilities with one set of numbers here. That's what I want to ask you to do calculation-wise. But bear with me here as we track through what's going to happen as we change this ability to discriminate with the test, okay? Because this ability to discriminate with the test is our beliefs about the reliability of this test and its relationship to the underlying things we're trying to measure, the uncertainties we have there. So we have a test that of the low ability people, only 20% will pass. Of the high ability people, 90% will pass. 12 plus 36 is 48. So 36 out of 48 will be of high ability. That's 75% chance. Remember, we started out with 40%. But now, if we see a positive test result, we're thinking, oh, I see a positive test result, very able people. Okay. What about see if I see a negative test result? Well, I got 4 plus 48 is 52. Okay, so 4 out of 52 is about 8%. I used to think that the chances of a high ability person were 40%, but having seen his negative test result, I'm now down to 8%. Okay. So the information down along this branch, down here, I'm going to believe something very different than I did at the beginning, which was I just had this vague notion of 60-40 in the population. After I've seen these test results, as long as I have, this is what I'm believing about the test results. Okay. So this is a way that you can use this truth table to think about your uncertainty, and just remember there's lots of things to be uncertain about. Ability, test given ability, ability given test. Now I want to play around with this a little bit and put this in a diagram because it helps. After a while you look at the numbers and you think, oh, I can see what he's doing there, but I really can't make any sense of how my uncertainty will change when there are things that I don't know, which is like I don't know how reliable the test is. Now this is another thing about probability stuff, or uncertainty stuff, is that the theory in game theory says people can come up with specific numbers which describe their beliefs. Okay, that's a specific willingness to bet. But usually in strategic situations, it's more qualitative. It's like, better than 50-50, not quite certainty, a little bit better than no chance at all. I mean, it's very sort of qualitative, kind of ballpark sort of picture. And these graphs can help sort of capture that idea. So what I've done here is I've put in a little box, and along this axis I'm going to put the probability of the ability. Okay, and if you like, this will be the probability of the state. Now down here what I did is it could be just the prior probabilities, or it could be with this little slash line and a question mark, like given some information from the test. Okay, but whatever it is, I'm going to put probabilities of the ability down. So I'm going to put probabilities of the ability along this axis, and they go from 0 to 1. I'm going to put probabilities of the test result, my uncertainty about the test result on this axis, which go, again, from 0 to 1. Again, they could be, what are the chances of a person getting a test result, or what are the chances of a person getting a test result given I know something about their ability. Okay. Now, I put on this, the next step here is to put our information that we started off with from that very first set of numbers, the 36, 4, 30, and 30. And remember what we had is we said there's a 40% chance of people having high ability. So this is where this number here comes. It's the 40%. Okay. There's a 90% chance that if you have high ability, that you'll get a good test score. And that's what this number is over here. There's a 50% chance that if you have low ability, you will have a high test score, and that's what that number there is. Let me put these labels in, I guess. So I've got those labels in your graph. And so the idea is we had these 3 bits of uncertainty. This is how we built up our notion of uncertainty. You say, we're not sure about the ability, but we can plot it down here. We're not sure about their test scores if they have high ability, or their test scores if they have low ability. We're going to plot those over here. Now, what I did is I put a dotted line at the 90%, and I put a dotted line at the 50% all the way along. The reason I want to do that is we're going to take probability weighted averages of those numbers, 0.9 and 0.5, okay, which are going to lie along a straight line. So I just want to get a benchmark here of a probability of 0.5, which is your chance if you have low ability of getting a good test result, and the probability of 0.9, which is your chance of a good test result given you've got high ability. Now let's go back to this 66 that we had, the 36 plus the 30. Okay? And remember, that was our way of thinking about the chances of getting a positive test result. If we take that number, where do we get the 36 from? Well, the 36 was 0.9 times 40. The 30 was 0.5 times 60. Okay? Just think of this, okay, that's the algebra. I can see what he's doing. But supposing I divide everything by 100. Okay. What do I have? Well, on here I've got my 66 out of 100, which is the chances of getting a positive test result, is really made up of 2 parts. It's a weighted average of the chances of getting a positive test result if I'm high ability, 90%, and a weighted average of the 50% chance of getting a high test result if I'm low ability. And what are the weights? Well, the weights are the 40 out of 100 who have high ability, and 60 out of 100 who have low ability. Okay? So this is just kind of a little algebraic trick. We're just saying, oh, the number 66 is the sum of these 2 numbers, but we can turn this around and break that 66 out of 100 into a weighted average, right? Well, we thought of weighted averages before, didn't we? We said, well, a weighted average of 2 numbers, a probability weighted average, is you take one number and then put them along a line and another number, and then you put the weight in between. Well, what we're going to do is, from this point here, along this vertical line, here's the 0.9, which corresponds to this one. Here's the 0.5, which corresponds to that one. This probability weighted average here is going to lie along that line. Okay, let's put it in. And where's it going to lie? Well, it's going to be 50% 60% on 0.5,
60 out of 100 on 0.5, and 40 out of 100 on 0.9, okay? A little bit more towards the 0.5 than it is to the 0.9. It's not quite halfway in between, but a little bit down. You got that idea? So what we can think of is that there's another bit of uncertainty here, which is the probability of a positive test result, which is the weighted average of two other numbers. The probability of getting a positive test result that you're given, you've got a high ability, the probability of a test result giving you a low ability. I mean, that kind of makes sense, right? There's people with high ability, good chance, people with low ability, low chance. You're not sure of the ability, well, okay, then the chance of getting a good test score is going to be somewhere in between that high and that low. But supposing we did that for every one of these numbers here, so for 0.3, 0.2, 0.1, all the way along, what we would find is that the probability of getting a good test result has got to lie along that line. Okay? The dot on the line corresponds to what we are believing now, which is the 66%. Okay? Now notice, remember, all we've done so far is remember at the very beginning, I talked about, okay, what's our prior probabilities? We don't know about the ability. We don't know what that is, 40, 60. And then I said, well, okay, what about test scores? What's the relationship between test scores and ability? And we thought, well, if you've got good ability, you've got a high chance of getting a test score, 0.9. If you've got low ability, a low chance of getting a test score, 50-50, lower, 0.5, okay? So we built up those three pieces, and then we started to calculate inverse probabilities. Along the way, we can figure out our probability for getting a positive test result, which is positive test result here is 36 and 30, 66. It's just a number that lies along the straight line between here and here. Okay? Now, this line is going to come from nowhere, out of the blue. It's just going to be a guideline. Okay? And don't worry about it where it comes from, but the guideline goes through this dot, and it goes through the origin. And you just straight line up like that. Okay? Now, the reason we're putting that guideline in there is the way to get the inverse probability is to take the intersection of that guideline with this 0.9. I mean, there's a whole bunch of theory behind that, but just supposing you do that, what do you come up with? This little dot here on the top is the inverse probability, that is the chances of getting a positive test result, having high ability, given you've got positive test result. Okay. What we said here is positive test result, 36 and 30, so we know it's going to be 36 out of 66. That's what that number will be. Okay? But the way we get it is by looking along this line here, intersecting it with this little guideline, and plunking up on this axis up here. Now, the reason we put it up in the top rather than down on the bottom is that when we read this probability statement, it says, remember, just think of it as, it's just language, okay? It's like you're learning a little bit of Greek or a new language. There's a piece that says, this is your probability of what? Well, the person's ability, is it, the ability being high, what's it going to be? And this is a given that they've got a positive test result. Well, given they've got a positive test result, it's like 100% chance that they've got a positive test result, so we want to be up here, not down here, because this is where down along this line is where you got 0% chance, okay? Okay. Get that idea? Now, let me go. There's two things I want to take out of this. One is the idea of the probability weighted average, which is this dot in the middle. Okay. And then anywhere along this line, say this number where the hand is right there, that's a probability weighted average of the 0.9 up there and the 0.5 down there, with the weight corresponding to that point on the probability axis. So it's like, if I wasn't really sure what the proportion of ability was, or probability of ability in my beliefs, describing my beliefs, I could still figure out it could be over here, but I am pretty sure about these numbers here. I can use this line to tell me what all those probability weighted averages are of the positive test results. Okay. Let me go to the next graph, which puts two of these things together, and it says, supposing we changed this whole test, okay? Instead of it being 50-50, we think of, now my beliefs are that, this is a more discriminating test. Low ability people, only 20% chance they're going to pass. you kind of crunch through the same exercise. We put in our probability of low, we put in our probability of high, we put in our probability of the ability, put in our little lines and our little dot, we draw the straight line between them, put in our little guideline, and find out the intersection point right over there. Now notice what's happened. This is the inverse probability we're interested in. This is our beliefs, given we see a positive test result about high ability. 66, it's 58%, not much. Over here, it's much higher. Okay, with the 80% sort of specificity, we're looking at 12 and 36 positive test results. So that's 36 out of 48, 3/4, 75% chance. Okay, way up from 40%. Now, the idea is when you don't know the numbers, if you can just you say roughly, well, I'm not even sure about this test ability. It could be up here, the sensitivity, or it could be down there. It could be 80%, okay, or up here, the specificity could even be better. I could be more specific test, could be more discriminating. Various combinations of these two, you can still work out what your inverse probability is. Okay, one last quick thing. I did the same thing with these graphs, only this time what I did is I kept the discriminating ability of the test, which is the uncertainty we have about the relationship between test scores and ability. Let me say that again. If we keep those the same, but we think, I don't know what the chances are of there being, a lot of able people in the population, or a large number of able people in the population, but I am pretty sure that this test will pick them out, okay, and it'll separate them out. Then what we get when we calculate our inverse probabilities is over here a small chance of having a high ability, even though you have a positive test result. Okay, so here we've got a test which 90% of the time able people will be able to pass, and 80% of the time low able people will not be able to pass. So it's not a bad test. Okay, you see a positive test result, you still shouldn't put too much faith in there being on this side over here, you shouldn't put too much faith in the person having high ability. Okay, that's because there are a very small number of people with high ability in the population anyhow. And this is called this idea of this is called a base rate fallacy, or it's not so much a fallacy, but it's incorporating that information about the proportion of people in the population, your beliefs about the chances of getting a high able worker. If there's only a small number of able workers in it, even if they pass the test, you shouldn't think of them as the person who's passed the test as being very highly able. For the same reason that we did it for the breast cancer thing. Okay, for the breast cancer screening thing, it was like very small proportion, 8 out of 1,000 have breast cancer. You see a positive diagnostic, you think, well, do I have breast cancer? Well, no, because there's going to be a lot of false positive signals there. Okay? So I realize, until you get your head around the construction of these graphs, it'll seem kind of mechanical, but what I want to be able to just look at them is saying, okay, here's the fact that this number here and that number there are fixed, they're the same in these two graphs, means my uncertainty in these two situations is the same as far as the relationship between ability and test scores goes. But what I don't know is how much ability is there out there. Okay? And if there's a very small proportion of ability, then when I see a positive test score, I'm not going to put a very high probability in the game tree of there being high ability. On the other hand, if there's a much larger chance of having high ability out there, then I'll put a higher probability on there being positive ability, given that I see a test score farther down the game tree. Okay, so next week next Monday we'll do mixed strategies, and then on the Tuesday we'll start to get into using this uncertainty stuff to talk about screening and signaling.